This lesson will cover polynomial expansion. The learning goal is to simplify polynomials by multiplying, and to use Pascal's triangle to expand polynomials. The success criteria is you can recognize when to expand to simplify a polynomial, and you can expand polynomials using Pascal's triangle. So a polynomial is an expression consisting of variables and coefficients separated by the four operands, operations being addition, subtraction, multiplication, division. Poly meaning many, nomial meaning numbers, polynomial being many numbers. Polynomials can be manipulated by combining them with the different operations. So recall that you can limit brackets using distributive law, expanding if necessary, and then combining like terms. This is a necessary skill when we are adding and subtracting polynomials. Also, remember that variables and exponents must be identical to combine them. These are like terms. So for instance, we have 5p to the power 6 q squared here. Is a like term with 5p squared q to the power 6 or 2q squared p to the power 6. A like term needs the same variables, same exponents. The coefficient does not matter. But what's important is both terms have p to the power 6 and q to the power 2. Well, here we have 5 and the order of p and q is the same. That's not what matters. What matters is the exponent of the variable, and you have the same variables. So these two terms are like terms. Also remember that a negative sign in front of a bracket will change the sign of everything inside the bracket. So remember, a negative in front of a bracket is actually a negative 1. And then we can distribute that negative 1 into that bracket. So negative 1 times 4, negative 1 times 3, and negative 1 times negative 2. And that will change the sign of all of your terms. So negative 4x squared minus 3x plus 2. Now we can combine these skills to simplify polynomials. So for example, we're going to simplify 1/2 x plus 1/3 y minus 1/5 over 5x minus y here. So the first bracket here, we have 1/2 x plus 1/3 y. There's really nothing we can do here. Both these are they're not like terms, and there's no coefficients in front of the bracket. So we can actually remove that bracket entirely. So it's just 1/2 x plus 1/3 y. And then we are going to subtract this bracket here. That's a negative, so that's going to change the sign of everything in front of that bracket or everything inside that bracket. And then we can combine like terms. So here we have two x's, so 1/2 x and negative 1 over 5x. We also have two y's. We have 1/3 y and plus y here. This is 1y. Now, by way of identifying like terms, just by putting squares, circles, and shapes around them, but you can use any method you want. You can color them, underline them, whichever way is best for you. Now, I like to rearrange my expression to have all of my like terms together. So I have 1/2 x minus 1 over 5 times x plus 1/3 y plus y. Now we are combining, subtracting, or adding and subtracting fractions here, so we have to remember the fraction rules, where we need common denominators in order to add or subtract. I'm not spelling that correctly. Where we need common denominators in order to add or subtract. So find common denominators, so find at least common multiple of the denominators. In this case, 1/2 and 1/5. The equivalent fractions for those for common denominators is 10. So 1/2 x will turn into 5 over 10x, and minus 1 over 5 is going to become 2 over 10x. We then have 1 over 3y plus, well, this is divisible 1y, so remember 1 can be seen as 1 over 1, and the equivalent fraction for 1 over 3 is going to be 1 over 3y plus 3 over 3y. We can then combine terms, so 5 over 10 minus 2 over 10, that's 3 over 10x, and then plus 1 over 3y plus 3 over 3y is going to be plus 4 over 3y. This will actually move off to the side, makes it easier to see. So that will give us again 3 over 10x plus 4 over 3y. Okay, your task is to simplify this expression here. Now we can also show that two expressions are equivalent by fully simplifying them. If they share all the same terms, again, order does not matter, only the sign and value of the terms themselves matters here. So we want to show that f of x equals g of x. So here we're going to simplify both of these expressions. So here we have 2x squared. Remember the brackets, there's no coefficient there, minus 2. And then we have minus 3x minus 7, because that subtraction is going to change all the signs of that bracket. And then g of x here, g of x is going to be x squared plus 8 plus x squared plus 4x minus 17. There's no changes here, it's just addition, and both brackets do not have coefficients. For f of x, we do have some common terms. 2x squared is alone, but we have plus 7x minus 3x, that is plus 4x. And then we have minus 2 minus 7, that is minus 9. And then with g of x, we have x squared plus x squared, that's 2x squared. And then we have plus 4x, so being alone, and we have plus 8 minus 17 being minus 9. So we can therefore say that f of x does in fact equal g of x. Now, when we're multiplying polynomials, we use the derivative property, expanding to then collect like terms. But remember that polynomials behave like numbers. If you're working with multiple brackets, expand and simplify 2 brackets at a time, as you'd only work with 2 numbers at a time. So for example here, we have these 2 brackets, but we have more than 2 terms in one of our brackets. So you may be used to using FOIL back in grade 10. You do, for instance, first, outside, inside, last. The same kind of variation of this method works here as well. It's just you're multiplying each term in the other bracket. So here we have 3a times 4a, giving us 12a squared. 3a times minus 3ab, so that's minus 9ab. And then 3a times 3b being plus 9ab. Nope, sorry, I missed a square here. A times a is going to be a squared. Sorry about that. And then we have 2b times 4b, that's plus 8ab. And then we have 2b times negative 3ab, so that's minus 6ab squared. And then finally 2b times 3b, so that's plus 6b squared. Now combining terms here, we only have 2 common terms, or like terms. We have the ABs, 12a squared and minus 9b. These are not like terms because, well, they do share a squared. This term does have a b with it, so these are not like terms. Same as with these b's over here. So we have 12a squared minus 9a squared b, and plus 9 plus 8 is plus 17ab, and then minus 6ab squared plus 6b squared. We cannot simplify any further here. We have no more terms. In our next example, we're going to simplify x plus 2 squared times x plus 1. Now what we notice here is, yes, we do have 2 brackets where we do have this x plus 2 squared. The one thing to keep in mind here is this x plus 2 squared is not equal to x squared plus 4. This exponent does not affect both terms individually here. When we do have a bracket squared, we need to then have 2 of those brackets. You must do a full expansion and FOIL here. So x plus 2 times x plus 2 times x plus 1. We now have 3 brackets, and you are required to only do 2 brackets at a time when expanding. So let's start with x plus squared times x plus squared. When you do fully expand that, it's going to give you x squared plus 4x plus 4. And then that's still multiplying the x plus 1. Now here we were doing a situation as we had above. Of course, it's in reverse, so you can do, for instance, x squared times x squared times 1, and a 4x times x, and 4x times 1, or you can think of it like a reverse, do x times x squared, x times 4x, x times 4. Whatever you prefer, both will always get the same answer. Let's just get through this. So we're going to have x squared times x, that's x to the power of 3. We have x times 4x, that's plus 4x squared, and then x times 4, that's plus 4x. And then we have 1 times everything in bracket, which is just a bracket again. It's also plus x squared plus 4x plus 4. And then combining like terms here, x cubed is alone. There's nothing else to go along with. We have 4x squared here and plus x squared here. That's plus 5x squared. We have plus 4x plus 4x. That's plus 8x. And then finally we have plus 4 on the end. Now, binomials is a polynomial with 2 terms. Now, thankfully there is a connection between the coefficients of expanding a binomial and Pascal's triangle. Now remember, Pascal's triangle is this structure here where you start with 1, 1, 1, and then you continue adding or continue placing ones down the side, and then every term below 2 terms above it is the sum of those prior terms. So 1 plus 1 is 2, and then 1 plus 2 is 3, 2 plus 1 is 3, and you keep it going down. Pascal's triangle does have a lot of connections with a whole lot of different things in number theory and algebra, so it is useful in that regard. The one thing to keep in mind here is that, well, we might say this is the first row, second row, third row. We actually refer to this as row 0, row 1, and row 2, row 3, row 4, 5, and so on and so forth. A good way to kind of remember is look at kind of like the second diagonal. This is going to tell you your row number. Now, if we look at these binomials on the left here, we have x plus y, that's power 1, power 2, power 3, power 4, and it shows their full expansion. What you'll notice is that the coefficients correspond directly to the numbers in that the relative Pascal row number. So for x plus y to the power of 2, look at row 2 here, and it goes 1, 2, 1, and the coefficients of the expansion are 1, 2, 1. The coefficients of row 4 are 1, 4, 6, 4, 1, so it's 1, 4, 6, 4, 1. Why is this helpful? Why would we do or use this to expand binomials? Because if you have, for instance, 2x squared plus 3 to the power of 5, that's 2x squared. Whoops, why is that not erasing? 2x squared plus 3 times 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 2x squared plus 3. We got 5 of these brackets, and you do these two, take that answer, expand with that, expand with the next bracket, expand with the next bracket. You do a lot of expansions here, and you be creating bigger and bigger brackets every time you do this. It is simply, it can become very tedious and can take a very long time. Now, obviously with higher orders, let's say you have 2 values in this power of 12, this gets just absolutely insane. So Pascal's triangle provides a quick, and in quotation marks, a quicker way of expanding and simplifying a binomial instead of working with 2 brackets at a time. So the other thing we have to realize here is look at the x and y variables here. So x and y, think of these as placeholders. The left term x, when you write out the full expansion, it starts at x power 4, and then x power 3, x power 2, x power 1, you can't see, and x power 0, which is not there at all because x power 0 is 1. But your left term is going to start to the power of your binomial and then decrease by 1 each term afterwards. The right term, the y, it instead increases as you move to the right, or you can think of the last term is in the start of y to the power of your binomial, in this case 4, and then decrease as you move towards the left. So a good way to remember that is left term starts at the highest exponent and decreases, and the right term starts at the highest exponent on the right and then decreases towards the left. So let's use Pascal's triangle here to expand 2x squared plus 3 all to the power of 5. So when you do this expansion, do the expansion with just x and y first. In some cases, it might seem as like a and b. And the reason why is we don't want to look at the 2x squared or the 3 just yet. Don't even look at those. Just think of it as x and y right now, and just write out the binomial expansion. So x plus y to the power of 5. It's going to start with, I will start with the x's, so I go x to the power of 5 whenever it loads. There we go. So we have x to the power of 5 plus x to the power of 4 plus x to the power of 3 plus x to the power of 2 plus x to the power of 1, which is just x, and then plus x, or plus x to the power of 0, which is not there, but we do have the plus sign there. Which means at the very end we'd have y to the power of 5. And then we want to decrease towards the left. So y to the power of 4, y to the power of 3, y to the power of 2, y to the power of 1, which we don't see the 1, and then y to the power of 0, which is non-existent, so we don't even write it. And now we're going to put our coefficients in. This is row 5. So row 5 is 1, 5, 10, 10, 5, 1. So 1, 5, 10, 10, 5, 1. Don't even need those ones there, but it's all right. Okay, the next step here is we need to then substitute the x and y values, which is 2x squared and 3. So that's our x, that's our y, and let's substitute. So we have 2x squared all to the power of 5 plus 5 times 2x squared all to the power of 4 plus 3 to the power of 1, which don't write, plus 10 times 2x squared to the power of 3 times 3 to the power of 2 plus 10 times 2x squared all to the power of 2 times 3 to the power of 3. As you see, it gets really tedious, very long here, plus 5 times 2x squared to the power of 1, which don't use, and 3 to the power of 4, plus 3 to the power of 5. It's a long process. It does take a while to write out, but trust me, it is way faster than doing the full expansion with the 5 brackets. All right, so the last step here is we just need to simplify, do the calculations here. The nice thing about the binomial expansion is after you do the expansion, there's really no terms in which you have to combine. In most cases, after you do the substitution and you simplify, do the calculations there, that's it. Okay, we have, well, now we have to apply the exponents to the coefficient 2 and x squared. So 2 to the power of 5, that's 32, and x power 2 to the power of 5, remember that's multiplication, so it's x to the power of n. We then have 5 times 2 to the power of 4 to the power of 16 times 5 is 80 times 3 is 240. X power 2 to the power of 4 is x to the power of 8, remember it's multiplication. And then we have plus, we have 2 to the power of 3 is 8 times 3 squared, which is 9, and then we have times 10, so that should give us 720, and x squared to the power of 3, that's x power 6. You'll see a pattern here. If the x's are decreasing by 2 each time. Okay, we are on the second 10 term. So it's 2 to the power of 2, which is 4, and then 4 times 27, because that's 3 to the power of 3. And then that's times 10, so that's going to give us 1080 x to the power of 4. Moving on, we now have 5 times 2, and that's times 3 to the power of 4, which is 81. So 81 times 10, that's plus 810 x squared. And finally, 3 to the power of 5, that's plus 243. And you'll see there's no like terms which you can combine here. That is our full expansion using Pascal's triangle.